Hi, how's it going? My name is Matt. I'm part of the advanced character team here at Epic. I'm pretty excited to be here today to show you some of the cool stuff we've been working on. So many areas of Unreal technology have advanced hugely over the years. We have Nanite and Lumen that allow us to represent highly detailed and beautifully lit environments. And with our awesome facial technology you've just seen and MedHuman Animator, we can recreate the subtleties of human performance and emotion. But we want to bring that same level of deformation quality to our character bodies. So currently, a typical body deformation setup for a real-time character is a combination of additional helper joints and sometimes corrective blend shapes that attempt to preserve the volume and silhouette of the character as it animates. In fact, our MedHumans use a helper joint system to do exactly that. But human biomechanics are extremely complex, and this type of setup is always going to be limited in what they are able to represent. So building a system that allows you to see the scapula moving underneath the muscles or the skin sliding over the rib cage as you raise your arm is always going to be a real challenge. So what we want is to bring our characters to life with the awesome muscle and flesh simulation that's available to us in Houdini. Now, these deformations look great, but the simulations are computationally very expensive. So what you see here is taking around a minute per frame to solve. So wouldn't it be great if we could have this level of deformation complexity but able to evaluate in real time? Well, what we are now able to do is to use machine learning to compress that simulation data into a format that can be evaluated at runtime. So you are looking at our ML character with deformations driven by full muscle, flesh, and cloth simulation from Houdini. It's running in real time and on PS5. It's taking around 1/10 of a millisecond on CPU for network inference, and as you see it here, around 1 millisecond on GPU for morph target evaluation. So this is a fully generalized model. We have not just trained it on the cinematic animation that we can see here. So this is our character. His name is Emil. He is an anatomically correct digi-double. He was authored from 3D scan data of head and body, and we also captured full body MRI data, and we used this to help build and validate our musculoskeletal system. This was taken into Houdini, where we work closely with our friends at Side Effects to set up full muscle and flesh simulation. Now, a lot of the Houdini tools we used are under active development. Even so, the results we're getting out of it are pretty awesome, and they're only going to get better in the future. And at this point, I also would like to thank our actor for giving us permission to use his digital likeness and for allowing us to create the simulation data that we use to train our different machine learning techniques. Now, each technique is referred to as a machine learning model. And this is a neural network that maps the value of some inputs to some output data. So for our particular use case, the inputs are joint orientations, and the output is the mesh deformation that matches our training data. For efficiency, we encode this deformation as a series of learned morph target shapes, and our network outputs the weights for these. So we have different types of model available for us to use in Unreal. Each uses a different ML technique, and each has their own strengths and weaknesses. There is not one single model that is appropriate for all applications. So we created 3 deformers in total using 2 of the models available to us. The neural morph model gives us really great results for flesh, but performs poorly for cloth. So for these areas, we used the nearest neighbor model, and this is able to better reconstruct the complex folds and wrinkles that we want to see forming as the character animates. So the total vert count for our character is around 315,000 verts, so it's fairly high res. Joint count is pretty lightweight. We have 91 bones, and this does include the fingers. Each of the models took around 50 minutes to train. So if you have a CUDA-enabled card, we can use GPU acceleration, so this makes training pretty fast. Now, we'll cover these models in more detail, but let's take a step back and try and get a high-level understanding of what they're actually doing. So each deformer begins with 2 versions of the same character asset. We have a very simple one. This is just a basic joint hierarchy and linear skinning, and this also becomes our skeletal mesh asset in Engine. Then we have the complex one. So for us, this was the muscle, flesh, and cloth simulation generated in Houdini, but really there are a ton of different deformations that you might want to learn depending on your technical and creative goals. So the basic goal is to learn the delta, or the difference, between the complex and simple example across a range of poses, and then compress that information into something that can be evaluated in real time. This is the training process. The result of this is an ML network and a series of more targets packaged into our ML deformer asset. When we apply this to our simple skeletal mesh and animate it, the resulting deformation should closely approximate our complex training example. Now, we need to give the models lots of examples of the character in lots of different poses so it can learn what the deformation should look like across a wide range of animations. This is the training range of motion, or ROM, and it's perhaps the most critical element of the process. Now, it's important to note that these models can only learn static deformations. They're not able to learn dynamic properties. But the muscle, flesh, and cloth simulation in Houdini are dynamic in nature. Muscles are affected by gravity and inertia, and folds in clothing will form differently depending on how you got into that pose. Now, this presents a problem because it means we're potentially trying to learn conflicting deltas for poses that have shared characteristics. And what will happen is that these will get averaged out, and sometimes the ML result can lack a lot of the clarity and the detail that we want to see coming through from our source data. So how do we work around this? So firstly, in Houdini, simulation parameters that look good for a continuous test animation are not necessarily the optimal setup for generating ML training data. So the goal here isn't necessarily for the simulation to look good in motion, but to minimize the differences in result for poses with shared characteristics. So we want to encourage folds and wrinkles to form in the same way, for example, when the character raises the leg. We want to simulate muscles relaxing and contracting, and we want muscle-to-muscle collision, but we don't want the effects of gravity or inertia to be present in our training data. There is an additional complication here too, and that is that the random poses in our training ROM mean that the pose difference from one frame to the next is pretty substantial. Now, we can't simulate this sequentially because the resulting velocities are too high for the simulation. So to work around this, we implemented a 10-frame warm-up and settle into each pose. So for each pose in our training ROM, we animate into position over 7 frames, and then we let the simulation settle for 3 before saving out the frame. So these additional frames were generated procedurally in Houdini. So let's look in detail at the models. So firstly, the neural morph model, the local neural morph model, tries to generate morph targets while looking at each individual input, and this results in many small localized networks. The global model, on the other hand, generates a single, fully connected network. Now, there are some big advantages to choosing local over global, and this should be considered the default approach. First of these is performance. If you look at the network diagrams on the right, each line between neurons represents a computational cost. So you should be able to see that as we add more inputs, outputs, or layers, the cost increases rapidly for the global model, whereas the local model scales much better to increased network dimensions. Global mode, however, can potentially look further than just around the bone. So in some cases, it can be better at learning deformations that are the result of multiple inputs. To improve local model reconstruction in these sorts of cases, we implemented bone associations, and this allows the model to consider multiple inputs in specific user-defined cases. So for the upper body, we created associations between the clavicle and the humerus, and this significantly improved reconstruction in the shoulder area while retaining almost all of the performance characteristics of the local model. The other key advantage of the local mode is that it will converge to a well-generalized model much faster and with less training data than global. So for the upper body flesh, we trained on around 7,000 frames, but I estimate we'd need around 50% more to get a similar result using the global model. The nearest neighbor model specifically targets cloth reconstruction. So cloth in particular, it's a real challenge because it's highly chaotic and very connected in nature. Even with a careful simulation setup, more complex garments, the nearest neighbor model is going to outperform the neural morph model every time. So this model starts with an initial PCA layer, and it's trained with a large set of random poses. So for the upper costume, this was the same set that we used for the flesh. Then on top of this, we add an additional layer of simulated fix-up poses. And these are taken from our target animation database. So this is the nearest neighbor data set. During animation, a nearest neighbor function evaluates the character pose and it applies the closest shape from that set to the character. So on the left is the nearest neighbor model with just the PCA layer active. And on the right, you can see how the additional nearest neighbor set improves the fold reconstruction. So to help generate the optimal set of nearest neighbor poses, we have implemented a k-means pose generator. So given a set of target animations, so typically these would be your game or cinematic animations, and a max pose value, it will generate a set of poses that most efficiently cover that animation space. We simulated our clothing for these additional poses in Houdini, and then we trained our additional nearest neighbor set using this data. So before we dive into Unreal and take a look at the workflow, let's get a high-level overview of it. So the first step is to generate the training ROM animation. The aim of this is to provide the training process with lots of examples of what we want the deformation to look like in lots of different poses. So currently, the easiest method of doing this is to use our Maya PoseGen tool, and this will generate a random animation. The second step is to generate the training data using this ROM. So we're going to use this in two places. First, we're going to apply it to our simple linearly skinned character, and we'll export an FBX of this. Secondly, we're going to apply this to our complex offline character. So for us, this was the muscle and cloth simulation in Houdini. We're going to run a simulation for each frame, and we're going to output the result as an alembic. The FBX and alembic are imported into the engine. We set our training parameters, and then we train. And once completed, we're going to test the results using novel animation. So we should always test using different animation to that which we trained on. And this allows us to understand if a model has generalized properly and is going to be able to perform well with any animation applied. If at this point there are particular poses that are not reconstructing well, we can go back to the ROM, we can add poses to give additional coverage, and we can run through the training process again. So getting to a good result is an iterative process. All right, so let's take a look at this in Editor. All right, great. So the first thing I'm going to do is I'm going to create our ML deformer asset. So once we load this up, okay, so the first thing to note, up on the top left, this is where we can choose which model we want to use. To the right of that, we can choose between training and testing mode. So we're going to start out in training mode. On the right is where we add pointers to our assets, and then here is where we can set various parameters for our network and training process. So the first thing I'm going to do is I'm going to add the skeleton mesh. I'm going to add our training ROM as an anim sequence format, and then I'm going to add our training ROM that is the imported alembic. So this came from simulation. So the geometry cache for that is pretty big. It will take just a second to load. All right, here we go. Now, on the left, we can see our training base. So this is our simple linearly skinned asset. And on the right is our target. So this is the thing that we're trying to learn, right? And this is what came from simulation. If I scrub through, we can see a matching training ROM running on each. And during training, what we want to happen is for it to learn the delta or difference between the simple and complex and then compress that information into something that we'll evaluate in real time. And we can see that delta visualized here with these green lines. So once we're happy that we have two matching ROMs, we can start setting our network up. So the first thing to notice here is where it says include bones. This is checked. So we're going to train using bones as inputs to the network. We could train using curves if we wish. So if we're using bones, we can only consider orientations as input and not yet translations. Underneath here, where it says bones 91. So by default, it's added every joint in my skeleton as an input into the network. Now, to get the best quality ML results, we want to reduce the number of inputs to the network as much as possible. So the easiest way to do this is to start by clicking this animated bones only button. and it's going to populate a bone include list based on the animation. So you can see we start off with 91, we're down to 25. That's pretty good, but we can go further. So you'll notice here it has included the roll or twist joints. Now the transformation of these can actually be described in terms of other input to the network. So we don't need to include these as discrete entries. So I'm going to go ahead and remove those. Oops, missed one. Right, and now from our initial starting set of 91, we're down to 15 inputs to the network. And this is the minimum set of inputs we need to describe the deformation that we are trying to learn. All right, so this is a critical step. Underneath here is where we can set up bone groups. We mentioned that earlier. Down here, we can choose between local and global models for the neural morph model. We can set the number of morph targets, the number of training iterations. Here we can play with the network dimensions. So increasing the number of hidden layers gives the network the potential to learn more complex deformations, but it does come with increased CPU inference time. Down here is the morph target compression setting. So we can change these after training. Modifying these values does not require us to retrain the network. And finally, under here, we can apply a mask to paint masks out for the ML deformed deltas if we wish. And this uses vertex color channels on the scallop mesh. So I'm going to just set the max training frames to 50. This will not generate a usable network, but it does allow me to show you all of the elements of the UI as they pop up. Right, so once we're happy with our settings, we're going to go up to the top left and we're going to train the model. Now what's going to happen to start with is we're going to cache a bunch of information for those frames. Once that's completed, it's going to go into the training iteration loop. So on the left, we can see this training iteration number increasing. And on the right, there's this average loss number. So this number represents the error between the current state of the network and the target deformation we're trying to learn. Right? So a smaller number basically means you're getting a better reconstruction result. So what we want is, as the iterations go up, for this number to come down. Now, initially, it'll start dropping really fast, and eventually it'll flatten off altogether. Now, we don't have to wait for all of the iterations to complete. We can actually click cancel. It will extract our morph targets for us. Because I canceled it earlier, it asks me if I want to save the partially trained network, so I'm going to go ahead and click yes. Right. Now, as I said, 50 training frames is not going to generate a great result, so let's take a look at our actual flesh deformer. So once we've trained, we want to go into testing mode. Over on the left is where we add our testing animation sequence, so we just have the cinematic animation applied here. Underneath is where we apply the deformer graph. This is what's driving the skinning, the morph targets, and it's recomputing normals for us. And I can scrub through, and we can see the animation playing on our ML deformed asset here. We can modify the weight and see the contribution that the ML deformer is giving to our character. All right, so the next step, I want to set up a blueprint for this. I have a partially set up skeletal mesh actor blueprint. I've assigned my skeletal mesh to the component. Down here, I've assigned the control rig and our deformer. So adding an ML deformer to this is super easy. All we have to do is add an ML deformer component and then find our ML deformer asset and apply it here. Now, if your blueprint has multiple skeletal mesh components, the way you create an association to a specific one of those is by using this component tag here. We would add an entry and then simply type the variable name of your skeletal mesh component in here. We can also stack multiple deformers on a single skeletal mesh component. But I'm happy with this, so I'm going to click compile. I'm going to close this down. So I have this blueprint dragged into the scene here. If I open up the sequence and enable the control rig, if I very simply, oops, why is that not working? Okay, I'm just going to switch. This is a live demo. Oh, dear. Oh, of course, yeah, it's a live demo. Right, never mind. What I really want to show you was we can manipulate the control rig. I can drag up the clavicle control. We can see the skin sliding over the abs. It's a fully generalized network. You can animate that. You can keyframe it in Unreal, and it looks great. I'm sorry, I can show it to you. So the most important part of this is the training ROM. So the models are good at interpolation, but they're really bad at extrapolation. So to take a simple example, if my game animation rotates an elbow from 0 to 140 degrees, we don't need an example for every degree of rotation in the training data, but it does need to encapsulate that full range. So if the model is reconstructing poorly, the two most likely causes are either you haven't used enough training data and the model hasn't generalized, or the animation is pushing the character outside of the pose space we trained on, and the network doesn't know how to handle that. So when this happens, the deformer doesn't just handle it gracefully. It won't just stop adding deltas. You're actually going to get some pretty nasty deformations. So it can be really easy to get caught out by making incorrect assumptions when you're setting up the training ROM. So you might have assumed, for example, a planar rotation for the elbows, but forgot that animators like to break stuff, and that performance capture data is often going to have small rotation values on all three axes. So if your training data hasn't accounted for these rotations, you're going to start hitting problems. So one of the issues we had was caused by excessive twist on the clavicles in our cinematic animation. So the training ROM assumed a total range of around 20 degrees, whereas the animation was pushing way past that to 70 degrees. So we can see this in our animation curves here, right? So on the left is our random data that we use for training, and on the right is the cinematic performance. And so you can see that the upper and lower bounds of the cinematic data extend outside of the training range, and we get the mesh collapsing in as a result. Now, in our case, we actually modified the animation rather than the training ROM, and this fixed our issue immediately. So for single animations, like in our case, it's actually pretty easy to debug this kind of stuff, because we can just bring the training ROM and the cinematic into Maya, and we can look at the anim curves, right? But we do need better tools in place to debug these kinds of issues against large animation databases. So currently, generating a random training ROM, like you see here, using our Maya PoseGen tool, is the easiest way of creating training data that we can be confident covers the full pose space of our character. So for each joint involved in the deformation, we're defining a min and max order rotation value for each rotation axis, and then the PoseGen tool generates a random animation based on those values. But this is kind of a blunt tool, right? It has no understanding of biomechanics, and we end up generating a ton of poses that are not physically plausible, and they're just not useful to train against. So here are some examples of this. So the tool has generated counter rotations along the spine. The biomechanical relationship between the clavicle and the humerus is not being respected. So generating training data can be a real challenge. So we want to make our training ROM as efficient as possible by reducing the number of bad poses. So in Maya, we set up a simple set-driven key system to drive the spine joints, and then we generated the random data using those attributes instead. So this ensured that the poses on the spine remain in a physically plausible space. We also ran a post-processing script to nudge the clavicle rotation values based on the orientation of the humerus. So by making the training ROM more efficient, contains less bad poses, we're able to use smaller training ROMs. So we are often asked about the structure of the training ROM. So does it have to be random? Can we use a continuous range of motion, maybe from a motion capture session? So the table above shows the dependencies between the model we can use and the type of training ROM. So for ML, we actually adopted a bit of a hybrid approach to this. So we use just under 7,000 frames of random poses. This goes the generalized model that allows it to perform well with a range of animations applied. We can even manipulate individual limbs using control rig, which I wish I had have shown you, and the deformations work really nicely, and the model is stable. We then refine that model with a small set of additional poses taken from various motion capture sessions. So currently, this is the approach I would tend to recommend, and that's to build a solid generalized model using your random data set, and then you can refine the result if you need by adding key hero poses from your gameplay or cinematic animation. Now, ultimately, we do want to reduce the need for using random data. And we want to move towards using smaller, more efficient structured ROMs of continuous motion. So we feel that this will offer a more intuitive approach for people to generate their simulation data, training data rather. And it will also bring secondary workflow benefits when using simulation data as source. The local neural morph model offers some support for this already, and we do expect to ship an example structured training ROM with 5.2 release. So there are a few points to consider in the pursuit of getting better results. We've covered most of these already, really, but one important point is that your simple skeletal mesh asset should still include twist or roll joints. So for those not familiar with rigging, these are additional helper joints that distribute twist in regions such as the upper and lower arms and legs, and it kind of removes that collapsing candy wrapper effect that we can see here, right? So without these, the delta that the ML deformer would need to apply to correct that pose is pretty big, right? So ML deformer is, in effect, a lossy compression. So with really large deltas like this, that error can become noticeable, and you might not get a great result. But by including the twist joints, the size of the delta we're trying to reconstruct is much smaller. Any error present is not going to be noticeable. So just to briefly cover performance, the table on the left gives a PS5 performance breakdown for each of the 3 deformers we used. To recap, we used the neural morph model in local mode for flesh and the nearest neighbor mode for clothing. The flesh layer running on the neural morph is super performant, actually, it's great. The nearest neighbor model has a slightly higher cost, and this is due to the additional nearest neighbor data set that increases memory usage and GPU time. On the right is a table of the network parameters that have the greatest effect on performance. So 0 delta threshold culls small deltas from the morph target set. This reduces memory and GPU time, but in some cases can introduce artifacts. Compression level is fairly self-explanatory. Higher numbers affects memory usage, but could introduce artifacts. Increasing the number of more targets gives the potential for better reconstruction results, but with a higher memory and GPU cost. And as we mentioned earlier, increasing the network dimensions gives the potential to learn more complex deformations, but at the cost of increased CPU inference time. Now, for the nearest neighbor model, PCA coefficient number and nearest neighbor data can be seen as broadly analogous to the number of more targets, and this affects memory and GPU time. So to sort of wrap up, given the right training data, the reconstruction and performance characteristics of the current models are actually pretty good. So the main challenges right now are around workflow and generating the training data. This has a big impact on accessibility and scalability. So what we have shown here today is achievable for a hero character, but we need to make workflow improvements to extend this out to secondary characters. We need alternatives to random ROMs. We need models that are less sensitive to being slightly outside of the trained space. We need support for multiple pairs of anim and geometry caches. And we need better debugging and visualization tools to help find the solutions to problems when things aren't working. We will be releasing this as a sample project with 5.2 later in the year. We will also be including all the geometry caches and all the source data. That includes the full musculoskeletal model that you guys can learn from, take apart, and hopefully repurpose for your own ML deformer projects. We would love for you to come and chat to us at a booth. You can get hands-on with this demo. You can change cameras, switch between musculoskeletal, flesh, and clothing layers. You can pause the action, and you can see the deformation result both with and without ML deformer running. And finally, I just want to thank everybody that worked on the project. I want to thank Side Effects for their help and support. You guys are rock stars. And thank you to you guys for your attention. Thank you.
what will be the first animated feature film coming from Mozambique called Kibwe, which is part of the Troublemakers project.
Kibwe is an animated movie about this young girl who grew up not knowing about her parents, and most of the things about her past were hidden from her. So now she's going on this amazing adventure to find out about herself.
Kibwe is a project that's being done mostly by me and my wife. She is in charge of set modeling, and she also co-wrote the script with me. And I'm directing, movie editing, animating. I'm even the mocap actor. And we also were able to hire a local storyboard artist, which helped us a lot in storyboarding and the concept drawings. One of the main struggles that we've been having over the years is that whenever we talk about our projects with potential investors, they don't take the project very seriously.
No one would believe that a Mozambican company, especially made by young people, would do this. So we struggled a lot with funding. That's why all this time we've been funding ourselves.
Whoa.
Wow. So for us, having the mega grants basically legitimizes our project. And because of that, our search for further funding will be easier in the future.
We don't have much time. We go through the lake, around the dam.
Kibwe is a very important project, mostly because the animation industry and movie production here in Mozambique is basically non-existent. Our local TV station would mainly show us content that comes from abroad, and we felt that our kids needed something that they would be able to identify themselves with. We tried our best to make our characters look as African as possible and as Mozambican as possible. And for us, that's why this project is even more important.
She always says one day she'll tell me everything.
We don't want this movie to be just made in Mozambique. We would like for it to be made in Mozambique by Mozambican people.
Working with local talent for us is very important because it means that we can prove to everyone that it's possible to find quality talent locally, and we don't have to outsource it to anywhere else. Most productions that are done here are basically done with the help of foreign investment, and that can most of the time compromise the vision of each project, and we don't want to have that compromise. Receiving the EPIC Mega Grants was a light at the end of the tunnel. It allowed us to tell the stories as we envisioned them to, and this for us is very important. We want to be able to put Mozambique on a map, and we want people to know where we are and who we are.
Isles of Japan. Located in the Sea of Japan, these mountainous islands are bursting with tales that are as fascinating as they are ancient. This remote area is not only entrenched in stunning environmental beauty, but also relics spanning across thousands of years of civilization. From lush green forests to small villages and even large gold mines, The Isles of Japan were an ideal location for our scanning team to explore. So whether you're looking for a variety of surfaces or stunning works of art sculpted throughout history, this impressive collection is ready for you to drop into your project right now. Visit the Megascans library today where you can get these assets for free with your Unreal Engine account.
There's a totally new way of making audio in UE5. We like to say that Metasound is to audio what the material editor is to texturing. Here we see a graph that creates a metasound. First, an audio file is randomly selected, then it's procedurally modified, and finally rendered for playback. With Metasounds, you get total control over the project's sound design, so you can drive next generation procedural audio
that he could add back into it, it would be to tell more of those stories.
In early development, we broke out 4 key pillars, which were authenticity, nostalgia, replayability, and player choice. We took those 4 elements and sort of based all of our decisions around those and made sure that if we were including a mechanic or making a design decision, it matched to one or more of those pillars and sort of didn't damage or go against any of them.
We wanted to keep this very based in reality and make it very convincing. So I would look up what types of foliage turned up in certain areas of the environment, and I would go on Google Maps trips to make sure that I was following the terrain very accurately.
We're reading these travelers' journals, and they would describe like these massive landscapes where you've got these huge prairies that just go for days. And then when we added the sky system and like the little bumblebees and things like that, it really just brought it all to life.
The 3D environments, while we wanted to make them really beautiful and lush, didn't look too realistic compared to the 2D characters that we had moving around the environment. So we chose a very flat graphical art style for the texturing.
For our art team, it just meant that they could, finally be hands-on. I'm not going to name names with the other engines, but this one really just allowed the artists to jump in and create without boundaries.
Moab, Utah. Located near the border of Colorado, Moab is home to not one but 2 of America's national parks. Filled with magnificent plateaus, breathtaking arches, and stratorocks that vanish into the horizon, Moab, Utah became an obvious choice for our scanning team to capture. The Canyons of Utah collection contains over 100 assets ranging from massive rock formations, small boulders, and arid vegetation. These assets were heavily used in the groundbreaking demo Valley of the Ancients to reconstruct the surreal and majestic beauty of the Moab Desert. The Canyons of Utah collection, along with thousands of other assets, are free to download right now with your Unreal Engine account.